welcome back. We're finally getting near the end of the renormalization of QED, and we have seen in the last 6 videos, right, a few times where I had to put a fictitious mass for the photon in order to avoid infrared divergences, right? So today what we're going to do is finally take a look at these infrared divergences and try to figure out a more rigorous way of dealing with them. And in that process, we'll also understand where they are coming from, right? So the idea today is to look at a very simple process, which is electron-positron scattering into muon and anti-muon, right? The muon and the anti-muon here. And the reason I'm choosing this specific scattering is a very simple process at 3 level, and also since I'm picking 4 different particles at the initial and final states, that lowers the number of different Feynman diagrams that contribute, right? By having the 4 external legs to be different, I lower the complication in terms of Feynman diagrams. We also look at these scattering at the ultra-relativistic limit, because that allows us to ignore the masses for these guys. And again, the idea is to simplify and look at the infrared divergences at the simplest place where they show up, right? And of course, many of the qualitative conclusions we'll get to here will be valid in more complicated cases, right? So let's take a look at these scattering. This is the only diagram that contributes at leading order, which means 3 level here, right? And you see that because I choose 4 different states, only the S channel really contributes, right? P is defined as the sum of these 2 momenta, right? P1 and P2. And in this case, since the S channel has P square always positive, right? I'll define a uppercase Q here. That is P1 plus P2 square, and that means that the center of mass energy square, or the Mandelstam variable S, right? This is always bigger than 0. And in this case, for the S channel, this P square is equal to Q square. But I'll use Q square during most of the calculations to highlight the fact that this is always positive, so you don't get confused by a P square that can be positive or negative in different channels. Right? Using the Feynman rules, we can write this guy like this, right? There's an I because we have 2 vertices there. There was a sign I already absorbed. This is just E square over Q square, and then all the Dirac structure, that should be just V bar of P2, gamma mu, U of P1, U bar P3, gamma mu, V of P4. So I already went ahead and contracted the photon propagator here. There's an I here with the 2 other I's, or 3 in total, 1 from the photon propagator, 2 from the vertices. You know, everything is already contracted here properly. If you have difficulties with this, maybe go back to quantum field theory 1 and take a look at the Feynman rules for QED and try to do it carefully, right? In fact, we did study that scattering, right? Specifically this one, electron-positron into muon, anti-muon pairs in quantum field theory 1, right? And we obtained the total cross-section, right? Here, what we care about is the ultra-relativistic limit, where we can take both the mass of the electron and the mass of the muon to 0, right? And when you do that, you obtain this for the differential cross-section, where you still have the angular dependency, right? So energy of center of mass square, 1 plus this cosine of theta, where theta here is the angle between these two final momenta, right? Which can also be written in terms of the charge, right? I can replace alpha by e to the fourth 64 pi square, and the rest is the same, right? Just to have the two expressions for those of you that prefer to see actually the charge here. So you can see the diagram itself is order e square, right? It means that the cross section will, I'll take these matrix elements square, so the cross section is e to the fourth or order alpha square, right? And that's the leading order for this scattering. I can also integrate in this angle theta here, right, to get a total cross section for the whole solid angle, right? And that I'll call sigma 0, and 0 here means the same as here, is the leading order contribution, right? I'll have corrections which we are about to calculate. So if I do the integral here, I'll just get a 4 pi alpha square over 3 times the center of my mass energy square, right? Or again, in terms of the charge, is e to the fourth 12 pi e center of mass square, right? So these are the expressions you get at tree level. And now we want to go to loop level, since we have this whole technology that we have been developing to calculate loops in quantum field theory too, right? So we want to go beyond what we could do before, right? So now, what are the diagrams that contribute at next to leading order, right? If you go and look at all the diagrams that involve just one loop, this is what you get. Let me get those diagrams here, right? So you have these guys right here. Now, you see, I have 1, 2, 3, 4 insertions of the interaction everywhere, right? So it would be easy to fool yourself and believe that now you would have something that goes like e to the fourth. So when I take the square of the S matrix elements, right, I would get e to the 8th. So the next order correction to these will be alpha to the 4th, right? But that's not true, right? Be careful with that, because in truth, right, if you're calculating a matrix element and you're including all corrections, right, these will look something like that matrix element I just wrote up there. I called it M0 here, right, which is itself order alpha, right? So this guy is order alpha. And then these corrections, right, which I called M2, right, which is order alpha square. If I was consistent, I would call this guy M1, right, but whatever, okay? And bigger corrections, right? But when you take the modulus square of this expression, you get, of course, the leading order correction, which is the one written right here, right? In fact, this is the cross section, but M0 square is going in there, right? And this is order alpha square. But the next to leading order is not this guy squared, right? There's also cross terms, right? There's actually this thing right here, M0 times M2 complex conjugate plus M2 complex conjugate M0, right? And then you have M2 square. So just by looking at the orders here, right? This guy is order alpha, this one is order alpha square. So this whole contribution is actually order alpha cubed, right? And then whatever comes next, because there are more terms here, right? Even cross terms between M2 and whatever comes next, M0 and whatever comes next, right? So this is actually order alpha fourth and so on, right? But the next, and here's the important part, the next to leading order correction in the alpha expansion is actually order alpha cubed, right? Which is the interference between the three levels and the one loop level diagrams, right? And this is what we'll be calculating today. In order to avoid calculating 5 loops here, there's a trick we can use, right? 5 loops is too much. I bet people already looked at the time of the video when they saw all those loops, right? But there's a trick we can use. All you have to do is to remember that in QED, right, in the real world, the charge of the electron is -1 in units of E, right? But and the charge of the muon is also -1 in the same units, right? But we didn't need to be like that, right? QED works for any charges for these guys. That means that if I can change those charges however I want, the cancellations, in general, the sum of all these 5 loops up here, will be a polynomial in these charges if I just leave them like that, don't put numbers to them, right? And whatever cancellations that happen between diagrams or at any order will be in terms that have the same powers of these charges and others, right, in your model, because in the case of this last loop here, you can have even other fermions besides the electron and the muon going around that loop, right? So we can use that trick and see how these guys behave in terms of the charges. So if you look at diagram A there, right, this is proportional to the charge of the electron here, right, and the charge of the muon cubed. B is the charge of the electron cubed, because now the loop is on the left side here. Remember, time is going towards the right here, it's flowing towards the right. So I start with the electrons and I finish with the muons, right? And now it's just linear in the charge of the muon, right? C is QE square here and Q muon square on the right. This is the same. So C and D are like that, right? And E is QE, Q muon times whatever is going around the loop squared, right? Let's call that QX for whatever is going around the loop, right? So we can avoid calculating most of these loops if we choose just to look at the coefficient of one of these 4 options here, and we'll choose this one, right? An important caveat is that if X is the muon, right, there's a part of this diagram that has a muon going around the loop, right, which actually contributes to that, right? But that's part of the photon self-energy, right? And we already saw, right, but if you go back to when we were calculating the photon self-energy, we already saw the full effect of that loop that can be included in the running of the charge, right? In any case, this loop was finite in the infrared, right? So we don't have to worry about that. So by choosing this coefficient of this polynomial, right, that is linear in the electron charge and take the muon charge to the cubed, we can worry only about diagram A, right? So now what we want to do is figure out the correction at this order, right? At next to leading order. Let's call this thing just I am gamma. This big gamma refers to the corrections of the vertex we're making on the right side. So it's a name for this contribution. And it will be the sum of this diagram, right? Which is the one we want to calculate. Plus, of course, we always, we know that since we're using the renormalized Lagrangian here, there's also the counter term contribution, right? So at next to leading order, I have to have these two diagrams. Here I was writing just the loops, but we know that the counter term also starts at order alpha square, because we have imposed condition that this counter term needs to cancel the divergences for these loops. So it starts at the same order, so it will appear here, right? We can, in general, write, right, without losing anything, we can write this contribution in this way. And the key point here is that most of this diagram does not change. I just have this small part here which is different from the three-level diagram. So we can write this in a very similar way to the three-level diagram if we encapsulate the full effect of the loop and the counter term in one small piece. Let's see how, right? Let's just write this as I E square over Q square, V bar of P2, gamma mu U of P1. So you see the left side here is unchanged, is this piece, right? And then the right part is where the change happens. And I write it like that, U bar P3, and I define here a new piece which I'll call gamma 2 mu of P, right? This can depend on the momenta going in there, times V of P4. So you see, what I did here is leave this as similar as possible to the three-level diagram. Even the dependence on the charge here is just E squared. That means there's another E squared in there, right, for these two extra vertices that are there, right? So I'm putting this whole loop here, and of course there needs to be a U bar going in and a V going out, and you know, everything else is the same, and this defines the change to the right side vertex, right? And so that defines gamma 2, and let me write it explicitly here. Now, this gamma 2 mu here, gamma 2 is the order of the correction, right, is just defined as delta F1 P square gamma mu, right? So why delta F1? Because we know, right, that this the QED vertex can be written in general, right, as something like gamma mu, right, which is a F1 times gamma mu, right, plus I sigma mu nu over 2m. In this case, the mass of the fermion here is the mu, right? P nu F2, right? Both F1 and F2 are the form factors that we have seen in the previous videos, right? And of course, this is the first correction to F1, right? There's a part that contributes to F1, and there's also a part that contributes to F2, and that's where I will define delta F2 over 2 mass of the mu, P nu, delta F2 of P squared, right? So this is the first one loop contribution to F1. This is the one loop contribution to F2. And of course, there's also the counter term, which is just delta 1 gamma mu, because every other correction, right, is already up front, right? So this is also included there. And of course, inside the delta 1, inside the delta 2 F1 and delta F2, there are extra powers of the charge because all the loop contributions are in there, right? So this is what we'll be working with. And we have spent, I mean, most of the last videos studying this guy, right? We have seen the finite contributions to F2, the divergences in F1, and so on and so forth. So we're able now to use a lot of the results we already have. In particular, F2, right? The one loop contribution to F2 was calculated 1 or 2 videos ago, right? And we found out that it is just the mass of the muon square alpha. So here are the powers of E that I said are in there, right? Over pi times some integral in the Feynman parameters. Let me just write that, the y, the z, delta x plus y plus z minus 1, right? Of this z, 1 minus z minus xy p square plus 1 minus z square m mu square, right? And we have seen that in the limit, right? First, this is infrared finite, right? There's no infrared divergence. I didn't even put a mass for the photon there. But also in the ultra-relativistic limit, where the p square is much bigger than the mass of the muon here, right? Delta F2 of p square goes to 0, right? It's easy to see that here. Just throw the mass away here compared to the momentum, and then you see that you have m mu over p square, right? And so this goes to 0, so I don't have to worry about this part, right? Will be small. It's infrared finite, and moreover, it's 0 in the ultra-relativistic limit, right? So we only have to worry about delta F1. Now, delta F1 was calculated in the last few videos using dimensional regularization, right? Which is okay. I mean, we could go forward with dimensional regularization, but the thing is, dimensional regularization kind of obscures the scales a little bit, right? It's not very clear where the UV and the infrared scales are, right? In the case, it's even worse, because in the previous videos, I used dimensional regularization to deal with the UV divergence, but not the IR. I was actually putting an IR cutoff, right? So now, in order to have the two divergences on kind of receiving the same treatment, we want to know delta F1 in the Pauli-Villars approach, regularization, right? Because now we have a soft cutoff for the UV and also a cutoff for the infrared, right? We didn't do that calculation, but you can find it. I'll put the references here in the comments for the videos, but you can find that in Schwartz and also in some old lecture notes of mine. I'll just write that here. So if I did calculate delta F1 in Pauli-Villars, with Pauli-Villars regularization, it would look like this. So it's proportional to E square over 8 pi square. Again, Feynman parameters that are omnipresent everywhere. Let me make them small because I have a big expression to write here. And then you get this log of z and this is the new thing, right? Lambda is a mass scale, it is the Pauli-Villars regulator, right? So this is the ultraviolet scale, right? And since we have seen Pauli-Villars regularization, you know what I'm talking about, right? This is just the mass of these fictitious Pauli-Villars particles I have to put in. In the denominator, I have our known quantity, right? This delta gamma square. I'll define it fully soon. But the mass of the photon, the infrared regulator, is hidden in here. And I also have this other piece here. Let me just write it. 1 minus x, 1 minus y, plus m mu square, 1 minus 4z, plus z square. Right, this is very similar, this part is very similar to what we obtained in dimensional regularization. Delta gamma square. And I have to close the brackets right here. And I think that's fine, right? So delta gamma is the usual thing. It's just z m gamma square minus xy p square plus 1 minus z square m mu squared. This is the general expression for delta F1. In this case, we'll be calculating at the S channel. So I'll just replace P square for Q square. For now, I didn't do it. So let me put P square here until we go to the, we specialize for the S channel, right? Now, we are interested in the ultra-relativistic limit, so we can get rid of the mass of the muon. Everywhere it's summed with the momentum, right? So I can just write this q square e square over 8 pi square. Let me copy this thing here, right? And then in here I can write the log z m gamma square minus xy p square z lambda square, and here same thing, right? I can not equal plus p square 1 minus x 1 minus y z m gamma square xy p square, right? So this is the expression we want to use. In terms of obtaining the counter term, right? We have seen that before, right? The counter term is defined as this contribution, right? Minus, in fact, this contribution, because when I add both of them, the divergence should disappear, right? But for this guy, I calculated that p square equals 0, right? So in this case, I just get minus e square over 8 pi square, Feynman parameters, right? And in here, I just get, right, this part goes away, and this part is just log of lambda square m gamma square. You see the two scales are here, right? The ultraviolet and the infrared scale, right? And this is an integral that is fairly easy to calculate. It's just a factor 1/2 since I eliminate all the dependence on the Feynman parameters. This is just e square over 8 pi square times half of the log of lambda square over m gamma square, right? So I have a counter term now, and I can even compare, right? I can compare these with what I got from dimensional regularization, right? If you take the delta 1 in the reg that we obtained before, right? You have to be careful because there I had a mess for the formula, right? So you have to go one step before the final calculation and take the mass to 0 and then do the integral. You get these will be just minus alpha over 2 pi, 1 over epsilon minus 1 plus 3/4 plus half of the log of mu to the square over m gamma square, right? Which can be written as minus alpha over 4 pi, 2 over epsilon minus half plus log of mu tilde square minus the log of m gamma square, right? Now if you compare both, right, this is just, I can rewrite this guy as just minus alpha over 2 pi, right? Just e square absorbs a 4 pi to become alpha, right? And you see this is the same with this half here, is the same minus alpha over 4 pi. So again, we are getting that dictionary between the 1 over epsilon divergence in dimensional regularization and the log divergence in Pauli-Villars, right? I'm just seeing this comparison right here. You can compare this part. Let me change the color here. If I get to select what I want, right? You just have to compare this part with the one that I got. Let me write it explicitly here. I just got minus alpha over 4 pi here, right? Times the log of lambda square minus the log of m gamma square. So this piece right here goes into that pink piece up there using the same dictionary we have found before, right? Like, so again, it's the same. The only thing that really changes is this number that is different from diagram to diagram, but it's always this equivalence between the log part, the coefficient of the log divergence, and the coefficient of the 1 over epsilon 1, right? It's the same number, right? So that's consistent when we are moving from Pauli-Villars to dimensional regularization. Okay, so going back to the calculation of delta F1, we see that we have these two pieces right here, right? One that is UV divergent, right? Divergent. You see here that the regulator for the UV is here. Another one that is finite in the UV. And also this piece is finite in the infrared, and this one is divergent in the infrared. In order to see that, you can take just this first piece, right? Just take the first term here and take the mass of the fictitious photon to 0. You get the following integral. I also did the integration in z here, so now I'm left only with the integration in x and y of this log 1 minus x minus y, because I integrated in z, right? Minus xy q square And then you see that these integrates, even if I take the mass of the photon to 0, this integrates fine to alpha over 2 pi. I'm not doing the integrals in detail here because otherwise we would lose too much time in the doing integrals, but you can follow similar techniques that we used in the first videos to do these integrals, right? So this will be just lambda square minus capital Q square. Remember, capital Q square is always positive, right? That's why I'm keeping it like that. And you see this is the 1 over 4 pi structure in front of the divergence that will cancel just fine with this counter term right here, right? The sign is okay. So you see this part will go away once I sum the counter term as we wanted. Right? Now the other part is, so this is infrared finite, right? UV divergent. This other piece is the opposite, right? Is UV finite, because you can see there's no Pauli-Villars mass here. But on the infrared, it's trickier, right? In fact, I have to be careful about a pole in Q square when I'm doing this integration. Again, I won't do that in details here, but that can be circumvented if you do the usual I epsilon prescription. So we exchange Q square for Q square plus I epsilon. In fact, that would be already here if we have kept the I epsilons everywhere from the start, right? And so the integral on that part will be just, again, the integral of, this is a common factor. Again, I have these two integrations, right? And the integrand becomes Q square, 1 minus x, 1 minus y. I'm not putting I epsilon in the numerator because it doesn't matter. It's only on the denominator that is important. M gamma square minus xy q square. And since we have a minus here, I'll have a minus I epsilon here. Right? And this integral is doable. And the answer is, I'll just write it here, alpha over 2 pi minus half the log square. So this is the log to the second power. Usually these integrals, if you do in Mathematica, for instance, you get these polylog functions, right? And so the second one is the log square of m gamma square over minus q square minus I epsilon. And then there's a log minus 2 log of m gamma square minus q square minus I epsilon. And some constants, pi square over 3 minus 5 halves, plus, and of course I'm taking here a series in m gamma, right? So there's terms that are order m gamma, but those I don't care because I'll take m gamma to 0, right? So these are the leading contributions to the infrared divergence, right? And now I can sum this part. So the first part of delta F1 coming from the integral of this log with the second part and also the counter term, right? Because both contribute. So I'm interested here in delta F1 of Q square plus delta 1. And this is alpha over 4 pi 3 halves. I'm just copying now this part, right? I took an extra power of 2 outside, so it's 3 halves plus the log of lambda square over minus q squared. The counter term, right? The counter term is written here. It's just minus alpha over 4 pi and this log. So plus the log of m gamma square over lambda square. I should have a minus here, but I inverted the argument of the log. And then this whole mess up here. Let me just write everything. Again, I'm taking an extra power of a half outside. So this guy minus 4 times this guy plus minus 2 pi square over 3 minus 10 halves, also known as 5, right? And that's it. Now I have the whole contribution, right, to that vertex. Remember, what we're trying to calculate here is really this guy, right? I already concluded that this does not contribute in the ultra-relativistic limit. So I only have really the gamma mu part times something. And that something is delta F1 plus counter term. And that's exactly what we just obtained right here, right? Now you can see that the UV regulator goes away because I'm adding the counter term. So this becomes just the log of m gamma square over minus q square minus I epsilon. By the way, I had to put an I epsilon here because to be consistent with the second part, right? Where I put I epsilon everywhere. And now I can actually take the limit of this epsilon going to 0. Let me just add everything up to get a simpler expression. This will be just alpha over 4 pi minus the log square of this minus, I can group now this log with this one, right? It's the same, and get a minus 3 m gamma square over q square plus minus I epsilon. I can also add all the numerical factors and get just minus 2 pi square over 3. And then this 10 halves with this 3 halves becomes minus 7 halves. And that's that sum. Now taking epsilon to 0, I have to remind myself that the limit of epsilon going to 0 of the log of minus q square minus I epsilon. So now it depends, epsilon is positive, right? I have to see which side of the log I'm approaching. In this case, with q square positive and epsilon positive, that means this is the log of q square minus I pi, right? And then I can plug that in, take the square of it, and substitute everything here and get. And then I can take epsilon to 0, right? Alpha over 4 pi minus the log square of m gamma square over q square minus 3 plus 2 pi I, the log of m gamma square over q square plus pi square over 3 minus 7/2 minus 3 pi, right? So these complex parts all come from take epsilon to 0 inside those logs. There are cross terms, and so it's just algebra. You can show this is the expression we wanted. Let me just put it explicitly here and put a nice box around it, because now we have to understand a little bit of what is going on here. And please note that I was missing a log here when I wrote this expression, right? So when going from here to here, it's important that this is the log of this, and not as I had before, it was like that, right? So I just fixed it. So now to understand this thing is interesting to go to the cross section, right? So now the cross section next to leading order is 1/4, because I'll do the average over spins, right? And so it's 1/4 of the sum over all the 4 spins of the initial and final particles, right? Times these, which I call just next to leading order correction to the matrix element square. And we have seen before that this is actually given by the interference between this new contribution, which I call m gamma, right, and m0, right? And there's 2 parts to that. There's this one, and also the one where I get m0 dagger, m gamma, right? As far as calculating these goes, everything is very similar to the 3-level calculation. But now, instead of having a Dirac matrix right here, let me go back to the expression for that matrix element, for that contribution. Instead of having just a Dirac matrix here, I have this complicated thing. But other than that, everything is the same, right? I have some Dirac indexes which are contracted here, right? So I'll get the usual 2-trace structure for that kind of diagram, right? That we can write down here in this way, right? So you can do it carefully, but it will be the usual thing that looks like e to the 4th over 4q to the 4th times the traces of the momenta and momenta slash and Dirac matrices that are in there. So it'll be just p1 slash gamma nu, p2 slash gamma mu, right? This is for the vertex on the left, right? The electron vertex. And again, I'm disregarding the mass because we are in the ultra-relativistic limit. And then there's a different trace for the right part of the diagram that involves the muon, which is p2, p4 actually. p4 slash gamma 2 nu, right? Because there's a Lorentz index to that. I'll put a prime here because this is actually the complex conjugate. I'll just specify what I mean by this prime in a second. p3 slash gamma mu, right? This is this part, right? That's why I put a prime here, because I'm taking the complex conjugate for this part. And of course, there's also this one, which is just the complex conjugate of this, right? I won't write everything again. Now, what I mean by prime here is really that I'm taking this guy, right? let me write everything. This is the trace of P4 slash times the complex conjugate of this, but I already used the fact that the properties of the Dirac matrices to be able to write this trace. So it's really only the delta F1 of Q square plus counter term that is I'm taking the complex conjugate of, right? Because gamma nu that appears in here is already, in order to build the trace, I already took the dagger of that. And I also have some other part, also complex conjugate, delta F2 times sigma alpha nu here. And this is multiplied P3 slash gamma mu. So the prime there means I took the complex conjugate of these coefficients here, but already in writing these traces explicitly, I did everything I could to remove the daggers from the Dirac matrices. Again, this part, right, will result, since I have two gamma Dirac matrices here, right, that will result in the trace of an odd number of Dirac matrices. So this will be 0 when I take the trace. And again, this is a reflection of the ultra-relativistic limit I'm taking. If I had masses here, then this part would contribute, multiplying the sum terms with the masses. But since I took the masses to 0, this ends up not contributing, right? So I only have this part, and that simplifies things a lot, right? Because now I can take this coefficient of this Dirac matrix outside the trace and write this in this way, right? It will be just delta F1 of Q square plus delta 1 complex conjugate of e to the fourth 4q to the fourth trace of this part times the trace of P4 slash gamma nu P3 slash gamma mu, and of course plus complex conjugate, right? Everything again. But now this thing we know, right? This is just the 3-level matrix element, right? With no corrections to the vertex, where I basically just moved the correction to the QED vertex as a multiplicative factor in front. This is just 1/4 of the sum over spins of what I called M0 square, right? And now if I add the complex conjugate, I'll have the same. The only difference is this coefficient, which would not be complex conjugated on this part, right? So the sum, right? Let me get this thing here. The whole next to leading order contribution will be, since I take this guy and adds with its complex conjugate, right, will be 2 times the real part of this guy times this one, right? So this will be 2 times the real part of delta F1 of Q square plus delta 1 times 1/4 of the sum over spins of M0 square, which is a nice result, right? I put a box around it, and it gets better because now this guy, this whole piece here is just a function of this Q square, which is always equal to the center of mass energy, right? So this is just a number. And it goes out of the phase space integration, right? When I put this inside of cross section, right? All that is left to do is do the phase space integration over the final momentum. And that does not change the center of mass energy. So this whole piece goes outside the cross section, which means now I can rewrite also the next to leading order cross section, right, of E minus E plus going to mu minus mu plus, right, as twice the real part of this, twice the real part of delta F1 of Q squared plus counter term times the leading order cross section, which will come once I do the final, the phase space integration with this element, right? So also in terms of cross section, I manage to get an expression which is a multiplicative factor, right? That's a pretty neat way of writing this, right? And now I can explicitly write the expression for 2 times the real part of this, right? Remember we had an alpha over 4 pi for these guys. This factor 2 turns it into an alpha over 2 pi. And now I just have to copy those logs that I had before. So it's a log square of m gamma square over q square, right? Minus 3, and now I only care about the real part, so all the complex parts that I had here can go away. M gamma square over q square plus pi square over 3 minus 7/2 times the leading order cross section, right? So I got this correction to the cross section, right? If you're confused, I'm just copying the real part of this expression right here down there. So this went away, everything else is the same, right, here. And this expression right here contains a very similar form to all infrared divergences, which will appear again and again in many contexts where you have infrared divergences, which is this log square here, right? These are known as the Sudakov double logarithm, which is characteristic of infrared divergences, right? And is the reason why they don't go away, different from UV divergences, right? It doesn't matter if I go and calculate, say, the cross-section next to leading order at some energy. Say I take one particular setup with initial center of mass energy, which I'm calling Q1 square, and subtract the same thing for a different energy. So now I'm looking at the difference between cross-section, the different center of mass energies. This log part goes away, right? So if this will be just alpha over 4 pi log square minus log square m gamma square q1 square minus log square m gamma square q2 square. This part actually you get rid of the gamma, right? 3 log of q2 square q1 square. all of these times the sigma at leading order. So you see that because of these log squares right here, we don't lose the infrared regulator even when talking about differences in observations at different energies, right? And that's very different from what happened with the UV regulators, where you only had logs and you had a similar situation to this piece, right? If you compare objects at different energies, then the regulator went away. And that shows us that these infrared divergences is very different in nature from the UV one. And since this is unobservable, even the cross-section is unobservable, that seems to be wrong, right? We cannot have a divergent observable, right? Not strictly, cannot be strictly infinite, right? And the key thing that called people's attention to what could be wrong here is that these Sudakov double logarithms were also appearing in other scatterings where you had infrared divergence. Specifically, you could calculate the chance for emission of a very soft photon, right? Just take, instead of producing electron positron going into mu minus mu plus, just think of mu minus mu plus plus an extra photon, which was very soft. Right? In that case, you also obtain this Sudakov double logarithm, and then that got people thinking, right? Especially what it means to differentiate the case where you have 2 muons at the final state and 2 muons plus a very soft photon. So let's just think of this cross section, right? So now I'm wondering about this E plus E minus going into mu plus mu minus photon, right? And these are the diagrams that contribute to this process at leading order, right? Keep in mind that this is the very lowest order diagrams that contribute to this process, right? But now there are some hints, right? You have 3 vertices here in both cases. So the cross section will be proportional to e to the 6th, right? And in terms of that scaling with the charges, you have QE here, which once you go to the cross section will be QE square, and Q mu, the charge of the muon square, which when you go to cross section will be the charge of the muon to the 4th, right? Which is the same as saying this goes like alpha cubed QE square Q mu to the 4th. Now, this is the leading order for this process, but look at the next to leading order thing that we calculated here, right? We got it by multiplying m gamma dagger, right, or m gamma times m0 plus complex conjugate, right? And this guy we choose, right, just to look at the part that is alpha square q e q mu to the cubed, right? That's the part of this guy we choose to look at. And this guy, the 3-level guy, is always alpha QE Q mu. So you see, both in terms of the alpha expansion and this charge scaling, right? The coefficient of these polynomials in the charges, these two contributions, right? The next to leading order contribution to the production of 2 muons and the leading order of the productions of 2 muons plus a photon scale with the same order in the perturbative expansion and the same behavior with the charges, which is another hint in the direction we want to go. So now we want to calculate this guy and see the form that these infrared divergence will take here. When I make this external photon, I had to define a new momentum here, the momentum of the photon, I call it P gamma, right? When this goes really soft, right? In order to do that, I'll do something similar to what we did before, right? In terms of the external legs, this is very similar to the 3-level E to mu production. The only new part is this photon plus this propagator, fermionic propagator here. So I want to write this as much as possible similar to a electron to mu plus mu minus scattering times a small part here that is new, right? Let's see how can we do that. So I'm writing this matrix element here in this way. So I'm forcing something similar to the thing we had before. So E square over Q square, V bar of P2, gamma mu, U of P1, right? This is the part for this left side vertex here that does not change, right? Already I contracted the propagator of this photon, right? And the right part that changes, I'm writing in this way, U bar of P3, right? This part. Then I'm defining a new guy, S mu alpha, because this piece here needs to have an index because there's an extra photon here now. V bar, actually V of P4, right? And of course, there's no avoiding the polarization of this photon that goes away, right? Which goes according to our Feynman rules as the epsilon alpha star. This is just the polarization of an outgoing photon, right? And S mu alpha now is defined as, so I observed every new thing here. I have a new vertex, so there's another factor of minus I charge here, and these two gamma matrices I need to put here, right? This is gamma alpha I over P3 slash plus P gamma slash gamma mu. Right? I have no mass here because, again, I'm taking the mass of the fermions to 0 in the ultra-relativistic limit. And I have to sum over the two diagrams, right? Because there's two options here. There's this one and this one, right? And the other one is just minus gamma mu I P4 slash plus P gamma alpha. And I have a relative minus sign between these two diagrams just because of fermionic Feynman rules, right? So now this S mu here is encapsulating all the new things, but I managed to put these in a very similar way to the diagram without this extra photon, right? The only new things are S and the polarization. Now I can use this to calculate the cross-section, and I'm putting the cross-section also in a very convenient form. So I'll write the cross-section of E plus E minus to mu gamma as 1 over 2 Q squared. Right? I have the integral over the phase space. Let's call this d pi phase space, right? This is the Lorentz invariant phase space. And then, of course, this, where m is this guy, right? And that I'll write, once I do the phase space integration, in this way. E to the 4th, 2 over Q to the 6th. And I'll define two objects here, which are very useful. L mu nu, X mu nu. Notice I'm not doing any calculations. I'm just defining and parameterizing these in a convenient way, right? The integral, let me define now everything explicitly. So the integral into phase space can be quite complicated. This is a three-body phase space because I have three final states, right? Is the product of J being 3, 4, or gamma, because I have P3, P4, and P gamma as the final momenta, right? Over D3 Pj 2 pi cubed, right? For each of the integration in each of these three momenta, 1 over 2 EPj, right? The final energy of each of those states, and then, of course, momentum conservation, right? 2 pi to the fourth, delta 4 of the sum over these three momenta, right? L mu nu, on the other side, encapsulates everything related to the left side of the diagram, the electron part right here, right? So this is just something that already appeared, right? It's just 1/4 of the sum over the spins of the electrons, electron and the positron, right? Let's like this, plus minus, right? Of V bar P2 gamma mu, U of P1 times U bar P1 gamma nu V of P2, which is just 1/4 of the trace of P2 slash gamma mu P1 slash gamma nu, right? Which you can calculate quite easily. Just take this trace and use a little bit of the properties of the momenta to write. This is just P mu, P1 mu, P2 nu, plus P1 mu, P2 mu, minus half of Q square G mu nu. So that's L mu nu. It contains only the electron part, which is quite trivial, right? We calculated these before, even in quantum field theory one, when we were actually calculating the electron positron, the production of muon, anti-muon, right? So this is the other part, L mu nu, and then X mu nu is actually where it is, right? Is the new part, right? And I'm including, when I write like that, right? You see that the integration in phase space is not here, right? So it must be in there, right? I don't need to put it here because the integration of phase space is over the final momenta, not the initial one. So I can easily take L mu nu outside the integral and include the phase space in X mu nu. And that's what I did. So now I have the integration in phase space, the sum over the spins of the muons, plus and minus, and also over the polarization of the photon. So I'm summing over the polarizations, right? And now I have everything on the right side of that diagram. So it's U bar P3 S mu alpha V of P4, V bar P4 S beta nu U of P3 epsilon alpha epsilon star beta, right? And we know that once you sum over the polarizations, you can use a trick with these polarizations, right? Because of the word identities even, that you can exchange the sum over the polarization for minus G alpha beta here, right? When you have this sum. So you can rewrite x mean u just as the integration of phase space. This minus is just this guy right here, times the trace of P3 slash S mu alpha P4 slash S alpha nu, right? And so that's x mean u for us. That's important, right? Now I have a bunch of restrictions over these two guys, right? In principle, I could write anything for them, but word identities, again, help us a lot, right? Just think of this intermediate photon, right? L mean u is essentially this, right? X mean u is essentially this, but I can just cut the photon in the middle, or just think what happens if I take P mu and contract to the right or to the left, right? This is constrained by a word identity that tells me that P mu L mean u is equal to P mu X mean u. If I contract this momentum P, which is the momentum of that intermediate photon, with any of these guys, these need to be zero, right? Just word identity again. And that puts a constraint for X mean u. That means, again, we have been doing this trick again and again. It's the same we did for the self-energy of the photon, right? That means that this guy needs to be written in terms of P mu, P nu, minus P square G mean u, times a function which I'm defining in this expression, which is a scalar function of P square, right? And now I can invert these. I just multiply both sides of this equation by G mean u, right? Just contract with G mean u on both sides, and I get that x of P square is just minus 1 over 3 P square G mean u. That's what I contracted on both sides of that equation, x mean u. So I can easily calculate this guy if I know x mean u, right? And that is good. Let me put a box here, right? And now I can use that in this contraction for the total cross-section, right? The cross-section is actually L mean u contracted with S, X mu nu there. So I can now, right, this is the cross-section. And L mean u, X mean u is, right, using everything I wrote above, right? L mean u I know is P1 mu P2 nu plus P1 mu P2 mu minus half of Q squared G mean u. This now multiplies X mean u, which I can write like that. So it's P mu P nu minus P square G mean u times X of P square. And you can see that when I'm doing that contraction, right, many times I'll get P1 contracting P or P2 contracting P, right? Remember that P is actually P1 plus P2, right? And that P1 square and P2 square are zero because I'm in the ultra relativistic limit, right? The masses of these guys are zero, right? And also that Q square, that's another important one, which is P times P, right? Can be written as P1 plus 1 plus 2 times 1 plus 2. P1 square is 0, P2 square is 0. That means that this is 2 P1 scalar P2. So every time that P1 appears multiplying P2 here, I can exchange that for Q square over 2. So all these products are either 0 or proportional to Q square. If you do the algebra here, you see that the whole product here is just Q to the 4th. Right? That you have to do the algebra, but it's not hard to believe that this is all just proportional to Q, and actually it's just Q square over X. I don't know why I put a P here. It's actually Q square. Right? Now with this, I can go back here, right, and write L mu X mu is equal. Right? Using this expression right here, I have another factor of Q square in the denominator, so this one becomes just minus, from this minus, Q square, right? Q to the 4th over Q square here, over 3 G mu nu X mu nu, which is a much simpler expression than what we had before, right? And that means that the cross section now, using this expression right here, right? I'm talking about the cross section of E minus E plus going to mu plus mu minus photon is E to the 4th over 2Q to the 6th, right? Times this one, so times minus Q square over 3 G mu nu X mu nu, right? Which is the same as minus E to the 4th over 6Q to the 4th G mu nu X mu nu. Now I know that the cross section at leading order of E plus E minus going to mu plus mu minus, which might seem unrelated to this other process, but bear with me, right, is E to the 4th over 12 pi Q square, right? That's an expression we have already seen at the start of the video, right? So now I can write this guy as, and that's the important part, right? Let me even copy it, right? As minus 2 pi over Q square, right? I'm forcibly extracting a part like that, right? I want to write this as a thing proportional to the cross section at leading order of another process, which is this one, E plus E minus to mu plus mu minus, right? Why do I want to do that, right? Let me put a box around this, and then we can discuss what I'm doing here now. Leaving the phase space inside of this X mu nu here allows us to actually write this in terms of a three-body decay, right? We know that suppose we had a photon, a massive photon of mass Q, right? So the mass of this hypothetical photon is Q. Then the three-body decay of this guy would be given by this, right? Just I'm calling this guy gamma star, right? Mu plus, mu minus, gamma, right? This three-body decay would be given by minus E squared over 2Q times G mu nu x mu. This g mu here would be the sum over the initial, the polarizations of this initial guy here, right? And using that, I can rewrite this expression as the following, right? Let me copy this here. I just have to arrange the factors in order to make these appear, right? This will be 4 pi over e squared q, right? Gamma of gamma star going to mu plus mu minus gamma, right? All the integration in phase space for these final three states is inside the x mu here, right? And then I have the sigma leading order here, right? And you can see that in the end, what happened here, right, is that I factored the annihilation of electron-positron into these three states in two parts, right? I have essentially here, which is this term times this, which is just the sigma of E plus E minus going into this gamma star times the decay rate of this gamma star into three bodies. That's what I managed to do by writing my cross section like that. And that's useful because now I can use all the technology that people have developed for calculating three-body decays to calculate this part of my cross-section, right? So this guy, I can just go back and read it off from the previous expressions, right? This is just E squared over 2q times the phase space integration. I'm just substituting g mu x mu here, right? Trace of P3 slash S mu alpha P4 slash S alpha mu, right? When dealing with three-body decays, it's very useful to go into the reference frame of the particle which is decaying, right? That means the gamma star here, right? In that reference frame, this guy that I'm calling gamma star has momentum p. I'm using just the definitions of the momenta I had before. It's decaying into a mu plus, mu minus. This is supposed to be a plus. Mu minus photon, right? With momenta P4, P3, and P gamma, right? And I'm going into the reference frame where this P right here will be just Q 0, 0, 0. That's why I'm saying, right? I know the P square is Q square for everything I'm doing. That's why I'm treating this as this strange photon, because it's an off-shell photon, right? With mass Q, right? Also, it's very useful, and you can find it everywhere people are dealing with three-body decays, to define these variables. On the left, you have some version of the usual Mandelstam variable. So the S is very, it's the usual thing. The other two are a little bit strange because instead of having 2 to 2 body, you have 1 to 3, but that's the usual definition. But more importantly, these X's defined on the right are the usual thing people use to do the phase space integration in this case, because there's these variables which are related to the fraction of energy, of the initial energy each of the final states is carrying, right, are very useful. In fact, I'm not showing that here. I think I'm giving it as an exercise, right? You can show that in that frame and using these variables, the phase space can be written in this way. Well, it's a very simple, I mean, much simpler than the integration over three momenta, right? You can write the phase space just in terms of x1 and x2, right? Beta here is just the ratio between my infrared regulator and Q square. So in the limit that beta goes to 0 is where I have my infrared divergence. And you can show that in that reference frame, and that's pretty useful, right? X1 right, which is defined as, let's just invert this relation, right? X1 is just 1 minus P3 plus P gamma square over Q square, right? If I open this, is just, I can rewrite P3 plus P gamma as P minus P4 just by momentum conservation, right? Because P is equal to the sum of the other three, right? Over Q square. And this I can show that is just P square minus 2P times P4 plus P4 square. Remember, in the ultra-relativistic limit, this is 0, right? This, in this reference frame, is just Q times E4, right? And this guy is Q square, right? So here I have Q square over Q square, which kills that 1 outside. It's just 1 minus 1. And I'm left with 2E4 over Q. And you see here, right, that X has this interpretation of the energy carried by this particle over the initial energy available for this virtual photon, right? Same for X2. You do the same calculation for X2, and you see that's 2E3 over Q for this guy. And you can show, again, pretty easily in that reference frame and using these expressions that the trace we want to calculate can be written in this way. You see, again, I'm writing everything in terms of x1, x2, and beta, right, which is my infrared regulator here, right? So now we can go back to the integrals, right? I just have to write the phase space like that, the trace like that, right? And look what happens when I go near the infrared divergence. You can see here that the infrared divergence comes from when beta goes to 0, right? So the only part that matters is this one, right? So the three-body decay I'm trying to calculate here will be given in that limit that beta is going to 0, but will be given by E square over 2Q, right? This comes from here. And now I put the phase space and the trace. The phase space is still up there, I can still see it, is Q square over 128 pi cubed the integrals 0 to 1 dx1, 1 minus x1 minus beta, but I'm taking beta to 0. Same up here, dx2 of this expression when I take beta to 0. This is 8e squared, 1 minus x1, 1 minus x2 times x1 squared plus x2 squared, right? This integral you can do, right? It's just simplifying it a little bit here, right? We won't actually do the integral, we just want to check when it diverges, right? That's the important thing for us for now. That dx1, 1 minus x1 dx2 and you can see it diverges near the two extremes of x, right? If x1 goes near 1 or x2 goes near 1, right? And that means the maximum for this axis, right? The maximum, one of the muons is carrying maximum energy, right? This is symmetric for x1 and x2. It's supposed to be symmetric between the muon having a lot of energy or the anti-muon having a lot of energy. So let's analyze just one of these two cases. Take the case where x2 is going near 1, for instance, right? In that case, what's happening here is that P4 plus P gamma square, right, which is Q square 1 minus x2, right? When x2 is going to 1, that means that P4 plus P gamma square is going to 0, right? And that in this reference frame, right, we can write, remember that x2 is 2e3 over q. So if x2 is going to 1, that means that e3 is going to e3 is going to q over 2, right? And then P, by momentum conservation, right? P4 plus P gamma is going to Q over 2, 0, 0, minus Q over 2, right? Just because in the reference in the reference frame of P, gamma star, P is Q 0, 0, 0, right? That means if this energy of the other muon is Q over 2, the energy of this sum should be Q over 2, but it should be on the light cone because of this relation. So the momenta should be minus Q over 2. So what's happening here is that the muon is taking a lot of energy, the maximum fraction of energy can take, which is half of it, and the anti-muon and the photon are recoiling against this muon, right? And the total momentum of the two is such that P4 times P gamma now, right, which is 0, right, since the square of the sum is 0, P4 square is 0, P gamma square is 0, right? So P4 times P gamma, which is E4, E1, 1 minus the cosine of the angle between these two guys, must be 0, right? in order for this to be 0. The P4 square is 0, it becomes square is 0. There's only two ways that this can be 0 now, is either the energy, I call the E1, but it's really E gamma, the energy of the photon, right? Either the energy of the photon is going to 0, or the angle here is going to 0, then the cosine is 1, and this is 0. In principle, E4 could be 0 too, but that takes us away from the ultra-relativistic. Remember, E4 is the energy of the muon. It makes no sense to take it to 0 because it, at minimum, should be the mass of the muon, which I'm disregarding here. Right? These two singularities have names, and we call this one the soft singularity, because it's when the photon is really soft, and this one the collinear singularity, which is when the photon is being produced on top of one of the muons. In this case, the anti-muon, because the other one is carrying a lot of energy and going into the opposite direction in this reference frame. Now, these soft and collinear singularities are generally the source for infrared divergences, and they will appear in every theory where you have massless particles, because you realize here how important it is that this photon, for instance, for the soft singularities, it's very clear that only massless particles can have energy that is really close to 0. And if you do a little bit of thinking on this angle, it's really only possible if someone to go to 0, if someone is really massless. Now, if we, instead of looking at this just where the infrared divergence is, we actually go and calculate this integral and take the leading terms in beta, we get the form of the infrared divergence, and this is how it looks, right? So you see very almost a deja vu like sensation when you look at that. Again, you have the Sudakov double logarithm here. The other logarithm is also here with even the same coefficient, right? So this is what made people suspect that the two divergences, the one coming from the next to leading order calculation of just producing two muons, was related with this one, where you're producing an extra photon. The total cross-section, I just have to substitute this in that expression that I had for the leading order production of two muons plus one photon, right? There's some numeric factors that cancel in front here. I have written this in terms of alpha. And again, the logarithms are there, and this is all proportional to the leading order correction of leading order production of two muons. Right? And that means now that if I add this new correction, right, with the one I had before for the next to leading order, so remember, this was infrared divergent. This is also infrared divergent, right? All the logs cancel away, and you get something that is infrared finite now. You see, all the contribution is coming from these terms, everything else cancels away, right? That means that the total cross-section, and here we're being really inclusive. What total cross-section means here? It means I can produce two muons or two muons plus a photon, right? I'm just adding up these two possibilities. I can have a photon there or not, I don't care. I'm just calculating the probability of producing mu minus, mu plus something. And this something can be a photon or nothing, right? That total cross-section, which is the sum of the leading order 1, order alpha square, with these two, right? The next to leading order 1, which is order alpha cubed, with the extra photon, which is also order alpha cubed, will be finite and will be given by this, right? This one is just what we had at 3 level without any infrared complications, plus the part of the infrared complications, which is now finite, right? And of course, there are corrections of order of a 4 or even bigger, right? So what happened here? What happened is by including the possibility of this extra photon, and that we call final state radiation, because this photon is coming from the final state. Suddenly, my infrared divergence went away, right? And this is a bit mysterious at first, but it gets better if I do a more careful treatment, right? Not just being so inclusive as to assume, oh, I just sum over those two possibilities, 2 muons or 2 muons plus a photon, because it seems at first sight that these are two different quantum states, right? That I'm summing over final states which are different. Doing inclusively like that, it's hard to see that part of these final states are not really different at all, right? In order to see that, you have to do something more careful, which is due to Sterman and Weinberg, which is to define something that is they call the Sterman-Weinberg jet, mu, right? Which is really not a muon, but a muon. It can be just a muon, but it can be a muon plus one photon going in the same direction with such small energy, either so close in angle, or even if it's far away in angle, with such small energy that I don't see that photon. And then you calculate the chance of producing this muon jet, which can be just a muon or this impossible to see photon. Of course, when you include the definition of the photon that can be possible or impossible to see, you have to say something about the experiment, right? You have to say something about how sensitive to soft photons is your detector. What is the angular resolution of your experiment, right? Because if the muon and the photon are going together, there's a minimum angle which your experiment can see. Anything smaller than that will be confused with just a muon, right? So if you include that from the start of your calculation, this is a much more complicated calculation, because then you cannot do anything at the matrix element level. You have to always go to cross sections, because you have the integration of your phase space gets really complicated, because you have to cut for small energies of the photon, for small angles between these guys. But then if you do that, you don't need that fictitious mass of the photon that we have put in, right? Because now you have a physical infrared cutoff. Any angle is smaller than your definition, or any energy for the photon is smaller than the sensitivity of your detector, will be cut off, right? But below those limits, there's really no difference between a muon or a muon plus one photon, right? Because you're not seeing that photon. Nothing is, right? In the experiment, this final state of 2 muons or 2 muons plus a photon are completely indifferentiable, right? So in that case, you get an expression that looks like this. So where this is the minimum resolution of your detector, and this is the minimum energy where of your detector that you detect that a photon could have to trigger your detector, right? And in that case, you understand where there's interference between these two final states and why the sum of them is finite, right? As you go to smaller and smaller energies, really this cross-section grows, and you can see how here, right? You even have the Sudakov double logarithm. Right here, you can see even one of the logarithms is really depending on the energy, and the other one is depending on the angle, right? And as you go to smaller and smaller energies, your cross-section grows. And that's something you actually see experimentally, right? This is a very common problem, especially in QCD, right? Where the gluon is massless, and you also have a soft collinear divergence. And you can see how that could go really bad, right? In this case, I have physical infrared regulators, but if I go to small, suppose I do more and more sensitive experiments, I will never have a real infinity, because no experiment, right, not even, no matter how good your experiment is, you never have infinite, angular resolution, nor be able to measure arbitrarily small energies. So this is always finite, but these logs can get big, right? And at some point you're doing a perturbative expansion in alpha, but if the logs get too big, right, then you can win over your perturbative expansion. So your theory becomes effectively non-perturbative, but not because your perturbative expansion is failing, not because your coupling is becoming big, but because these logs are becoming, your couplings become, the logs are becoming big instead of your coupling becoming big. And that led to a lot of development, right? People have developed a way of resumming these logs, and that's what's called the soft collinear effective theory, in order to deal with this extreme production of jets in this direction, right? Collinear with your massive particles, right? That's not a subject we are touching in this course, but it's something that you should know to exist, right? So that's it for today. Thank you, and see you on the next video.